light in order to arrange this, UA, this is University of Hawaii, researchers at University of Hawaii did it. But I can tell you that bubbles are mostly nuisances in optical tweezers, and that is the way we thought of them, because so they are used as, this is of course something different than what I'm showing you. This has been pitched as micro robots and all, where it can actually be generated and simultaneously manipulated using light. However, this was a very special. So this paper is, this thing that you see was developed, I think around 2010, 2011, about more than a decade back, where this microlithography thing that this bubble can actually facilitate was not quite known. And I can tell you, as I was saying, that we perceive bubbles as quite a nuisance, because what happened was in optical tweezers, you have this very, very strongly focused beam of light. And at times, if you have anything absorbing in the path of that light, it actually heats up a lot. And as a result, you actually get these bubbles, which we thought was just irritating. So however, this is something which we actually saw later, that this paper, which was essentially published, I guess, in 2012 or something, 2013. And we found this later, where we actually saw that this same sort of a bubble had been actually used to write down CHUO, which is this Chuo University at Tokyo. Researchers had actually, on the substrate, they had, this was some kind of a gold substrate. And these objects that you see were actually gold, no, these were, I think, cadmium selenide quantum dots, okay, which actually arranged in this nice circle at the base of this bubble, which was grown. It was called ring formation. It was published. But I can tell you our story. And it also, this of course came later. This is what we had developed almost the same time, and probably 1 year later, where so here what these researchers showed was you actually got discrete patterns. So you can see these nanoparticles are sitting at some distance with respect to each other, right? These are all individual nanoparticles that you actually see. This is not really nano, I would say these are microparticles, but everybody calls everything nano these days. However, these are microparticles. But then what we showed after this accidental discovery, which I'm going to talk to you about right now, is you could actually make continuous patterns. So this was published in 2013. It is actually one of the most cited papers of our lab since we started it around 2010. What we saw for the first time was it was not, so because if you have just discrete patterns, a lot of applications are prevented. So you cannot really make circuits, right, with not continuous patterns. So, once we could manage to do this, that opened up a lot of new stuff. But how did we do it? So we were actually, my student Basudev, as I was telling you, he was working on these soft oxymetalates, which were given to us by a colleague in chemistry, Shomujit. I should have mentioned his name. So Shomujit Roy is the main one of the, two people, if I can consider myself and him as the two PIs who kind of, developed this together. So Shomujit gave me the material and we developed the technique. So, however, it also, both of us are, completely synergistic to each other, in the sense that without the material, this cannot work. And of course, the material is useful because we can make it work this way. So what we were trying that time, so these soft oxymetalates, these forms are soft oxymetalates, which are some kind of liquid metals, okay? And they actually they absorb from this wavelength of 1064 nanometer, which is typically wavelength that one employs in optical trapping. And the reason that you have this wavelength is it does not damage biological cells because they don't absorb so much from at this region. Okay, so they get excited, they go to a higher energy state because of this ligand metal charge transfer. And then the advantage is that they also form these stable dispersions in water. And what we were trying that time was to see these things are very flexible. So they are actually, the basic basal unit is nanotubes, but then they sort of again self-assemble and they make these long flakes of flexible polymers. And we were actually investigating shape memory. We were seeing that if the laser beam could sort of, bend or twist or do something, then if we remove the laser, could it come back to its original shape? And then one day Basudev came and told me, we are seeing these irritating bubbles which are getting formed. I'm trying to throw them away because they're not allowing me to see anything, and I'm not being able to throw them away. I said, what? So he said, yeah, because if I'm moving the laser, the bubble is going with it. So I said, wow. And then he said, and I'm also seeing that some strange deposits are, forming at the path of the bubble. I said, wow, so what is this? And then we looked at it a little more in depth, and we saw, yes, what happens is these soft oxymetalates, when you take a dispersion, some of them just, so this is like a very, very simple sample chamber, which is just two cover slips, microscope cover slips, which is stuck to each other using some sticky tape, or at times we don't even put sticky tape. We just take a drop of some, water or liquid, some substance where these things are dispersed. And then what happens is some of them will stick to these surfaces, right? Either this or that. Then you come with your very tightly focused beam. When I say tightly focused, that means the focal spot is only 1 micron. So you can understand the intensity is enormously high, right? Because intensity is power by area. So if you do 1 micron square, it's 10 to the minus 12, and that's in the denominator. Even if you use like 100 milliwatts or 50 milliwatts of power, you can actually get gigawatts per meter square types of intensity, huge intensity. So what happens is some of these would stick, and then when we came in with this focused light, it would get so hot that the water starts boiling. Now you remember this entire thing is like a drop of water, which is like about, say, 20 microliters of volume. But of that, I am actually hitting this small, and this surface is, I would say, something like a few mm. I mean, no, it's a cover slip, right? So it's about 15 mm, 20 mm long. I give a drop of water, which occupies about maybe an mm or two in, the drop of water. The diameter is about maybe an 1 mm or 2 mm. Of that, I am only exciting a 1 micron region. The entire water around it is very cold. So the bubble can only form. So can only form at the point where the laser is focused, right? And it's like a phase separation of air and water, because inside it's air. And what happens is it prevents the entire water from boiling. Okay, so what we have is that this bubble, one side of it is this laser beam, which is hot, and the other side is in contact with the substrate, which is cold. Now, if you think of it, surface tensions is just like this, right? This is the laser focused, and this part is hot, this part is cold. We call this the hot spot. So what happens is, because temperature and surface tension are inversely related, this part has low surface tension, this is high. This part wants to expand, this wants to contract. And if that happens, this part of the bubble wants to grow bigger, this wants to shrink, and that causes a stress to the liquid. It displaces water. It displaces there, pulls in here, and as a result, you get a flow. And whatever material is there in the water comes and sits at the base of the bubble, because it is blocked by this cover slip here or microscope slide here. So what you get is what I showed just in the picture of the work by the Tokyo group, a ring, which is just nothing but the impression of this surface, a 2D impression of the bubble surface on this microscope slide or cover slip. And that is what we saw. And this is exactly how it works. So you see, I'm coming in with this laser beam. I'm doing all kinds of stuff to put it into this microscope. Then what I do is, this is a translation stage. I manipulate this translation stage manually or automatically by whatever means. And you see this bubble. You see this bubble is actually formed. See, there is this pre-existing trail, and I'm moving this laser light. This bubble is nicely following it, and there you see this, like the wake of a jet plane. So if the skies are very clear, at times you see two tracks of this jet plane, right? With very, very fast flying planes, which are, almost at the velocity of sound. So you actually get a lot of nucleation of these water droplets there because of shock waves produced and all that. That's a different phenomena, but it looks exactly like this. You can understand. And what happens is, these patterns that we produced essentially depend on the size of this bubble. And what we saw is, then of course we dug more deeper, and this is something which I'm telling you out of like hindsight, out of what we know now. That time we were thrilled that we had this. It was fantastic. We could make whatever we wanted. We had, we had that time, these integrated PhD students, two of them had joined my lab. One of them was Shubhra Kohli, whose picture I showed you. So that was the first year they were in, right? They were very complete novices, greenhorns, no experience. They were fascinated. And we had this very cheap, 60,000 rupee microscope from an Indian company. And one day, Shubhra Kohli, or I think it was Shubhajit, he actually drew a house. He drew the picture of a house by the same thing. Okay, so what we saw, of course, was using our very, very expensive Zeiss microscope. But both of them, Shubhra and Shubhajit, they actually could get this whole thing done on a very, very low cost microscope with almost nothing. Just you needed, uh, some light to see your images, some camera associated, needed a microscope objective 100x, and you needed some absorbing some medium that was absorbing, and you could do whatever structures you want. Then we wrote ISA. After that, of course, we now know that there are two ways in which you can generate this bubble. And I think I've shown you two ways. So this first thing that I showed you, where they wrote chuo. So that uses an absorbing substrate, where the substrate itself is of gold or something else, which absorbs, which gets heated up, because you actually come in with so there's something called plasmonic resonances in these metal insulator structures. And if you come in at the plasmonic resonance of gold or silver, whatever, you get enormous amount of absorption, which causes heat. And because it's plasmonics, you can actually focus to extremely small spots. So I can see it. You can get a 1 micron bubble size in these cases. You need laser powers of less than a milliwatt at times as well. The next other strategy is to have what we did, is absorbing particles in solution, in dispersion or whatever. So they would come and stick to your substrate, and they would absorb, and they would create a bubble. So here what you see is the resolution. Of course, this has lower because the focal spot itself is lower. Here it's 0.5. It's very close here. It's about 0.65. But remember, it depends on the wavelength as well, because the size of the spot depends on the diffraction limit. It's limited by something called diffraction limit. We use about 1064 nanometer 1 micron lasers, which means our focal spot size is about 1 micron. So we have all kinds of different applications. I'll show you them later. At the moment, these three things is what I'd like you to sort of consider. And this last one, because making a gold-plated cover slip is not cheap. You have to use e-beam or something like that to make that whole surface, whereas this costs nothing almost. You just take your material to be patterned, and lo and behold, you get very, very nice structures. Okay, and what are the things which control the pattern width? Obviously, the size of the bubble, and that depends on several things: laser intensity, how long you irradiate your substance, your material, your solution or dispersion with the laser, how fast you move. Because if you actually wait, the bubble gets bigger. Okay, but if you move the stage very fast, the bubble cannot grow big, right? And therefore this controls the time the laser spends at a spot. If you want to make thicker, so I didn't talk about thicknesses yet. If you want to make thicker patterns, then you have to wait for longer times. And of course, concentration, because if you have high concentration dispersions, you get material coming in much faster. And then if you have low concentration, if they come in faster, you can have bubbles over a shorter time. And if you have bubbles over a shorter time, then again, for the same time, for low concentration samples, you get smaller bubbles. For high concentration, you get bigger bubbles. Okay. So then there are two types of patterns also, as I have said. One are discrete patterns, and you see that literature, these have been formed of these cadmium selenide, zinc sulfide, quantum dots, gold nanoparticles. I think this was interesting, where in the center you actually find this gold nanoparticle sort of pattern. It's on the surface, and then here you have darkness. So other places, so this was done, I think, using a higher order Gaussian beam, like a Lagarde Gaussian beam or something, which has dark. I don't remember actually, to check it out. It was with I think it was done with an interference pattern of sorts. Where in the bright fringe you got a bubble. You got these things coming in, sitting, and here there was a gap. They called it a nano gap, and again here you had accumulation. So this was, I think, both of these were done with polystyrene beads, but then these are not that useful, because making continuous patterns helps in a lot of applications, especially in electronics and all. So these are examples of continuous patterns. So by the way, let me tell you that at the moment, other than us, there are these two groups which are very, very absorbed in this. One is at the University of Texas, Austin. So that is by a Chinese professor called Professor Zhao, I think. And the other is in BIV. So it is this university in Israel. Okay. So that is the group by Professor Speisman. And there are other co-workers as well. So Zheng and others. I'll tell you in detail at the end. I think I will refer to you about this paper we have written, where you get all details about what is going on at the present state of the art. So these are some continuous patterns. This was made by us. This is again made by the Speisman group. You can see this is made of some silver. This was made by polyaniline. This is very interesting. So we made electronic circuits out of this. Polypyrrole polyaniline. This was again, I think, the CDSE quantum dots. This is fantastic, right? I'm sure everybody recognizes this face. This was done by the Zhao group. This is Chaplin. This was a barcode, which was again done by the Zhao group. So you can see how fantastically, developed this technology is. You can make a face of Chaplin. If you read their paper, you can actually make, I'll tell you the paper in the next slide, they have actually made Mona Lisa. So how have they done that? So, so before I come to that, there is one issue which is very important. That is, while in our cases, we make continuous patterns very easily. If you actually want to make patterns using silver or something, there is a problem. And what is the problem? So this is something that the Speisman group showed. This is in ACS Applied Materials and Interfaces a couple of years back, 2017. So what they saw was that if you had sort of, if you wanted to pattern silver, then if you have this bubble sitting, what happens is you have that deposit of that ring, right? And it grows in time. And what happens is when you move the laser focal spot, the bubble gets pinned. It cannot follow the spot because there is that obstruction of that ring of material deposited, right? So then that is why you do not get continuous, patterns. So, you would take the thing away and the bubble would jump. By the way, there is a very important question here. Why does the bubble follow the laser? Okay. So one thing that you can obviously understand is that if I've taken the source of heat away, I cannot have a bubble at the previous position. So now there are two possibilities. One is that you basically have a new bubble, or second one is that the old bubble can follow. Now, energetically, having a new bubble costs more energy. So you know that everything in nature is based on the minimization of energy. So in order to, if I look at, think of that in that way, this bubble will actually follow. It is energetically less costly for a new bubble to be formed. But of course, this is the qualitative way of explaining. You can actually use fluid dynamics and show that the flow generated itself would cause the bubble to follow the laser spot. Okay, so then what happens is you basically have discrete patterns, and how did they solve it? So they just modulated the laser. They turned it off and on, off and on, off and on. And they did it. This was not a pulse laser because pulse lasers typically are modulated too fast for the bubble to react. So this was done for the continuous laser at 1 kilohertz modulation, off on, off on. When the laser was off, the bubble would just rise momentarily, and then you catch it again. Right? And then you see how beautifully continuous spots you get. In fact, this is what we have tried also, and we've been able to pattern silver, I think, in the same manner, but more about that maybe later. But then, so what happens in our case? What happens in our case is we never had this problem when we tried to pattern these SOMs. And the reason probably is, by the way, this part is not quantitatively explored yet. We have not had a clear model of what happens. So what we see, however, experimentally, is that once you have a pattern formed, that pattern is actually crystalline in nature, which is fascinating because SOMs themselves, soft oxymetallate themselves are amorphous. But somehow, when you actually pattern them due to this bubble, there is a phase transition. What we think of is something like, so these are like, technically speaking, these are like these Baxter type phase transitions, but then that's all jargon. So what I would like to tell you as a simple experimentalist, what I think is, because you have these SOMs which actually start melting because of the high temperature, when you suddenly move the source of high temperature and they are exposed to the temperature of the water, which is at room temperature, they suddenly get this thermal shock and they freeze. And that basically causes them to undergo a phase transition, which we clearly see by these diffraction, TMs, diffracted spots. This is typically indicative of the formation of some kind of order, crystalline order. You have diffraction pattern. That's why you have these nice spots here. And that was also confirmed by my friend Shurajit Dhara in his lab at the University of Hyderabad, where we did this birefringent spectroscopy. And you could see that there is some change of polarization around this track, which is clearly indicative again that we have some kind of crystals being formed. So there is a phase transition. In our case, we do not have this problem of because the salts are already molten. Okay, so they're not hard. When you want to pattern these, nanoparticles, metal, these they will just obstruct. Here the bubble can easily pass. That is what we feel. So what are the applications, however? So the applications are fascinating. One of the most important is to make electronic circuits you can very easily understand. So this is what we had done. So we took some conducting polymers, and so conducting polymers, are the basis of flexible electronics. And so we took, very interestingly, we took monomers of pyrrole and aniline, and then in the process of patterning itself, we saw that they became polymerized. We patterned them in these nice hallbar structures, and we actually got, so if you see, we measured the conductivity, this is of polyaniline, we got about 450. Okay, this was far higher. So if you want to buy commercial polyaniline from Sigma Aldrich, you will see it's less than 1. We got about 500 times higher conductivity. Why? Because we actually doped it in the process of patterning. This is a complicated in the oxidation reduction reaction, redox reaction, which happened. Essentially, the SOM, when it gets excited, it gives away one electron, and the pyrrole accepts the electron, and essentially you get the formation of something called MOO2. Okay, MOO2 is a metal, and that gets formed in the process, and that increases the conductivity tremendously. So the Spiceman group, they could pattern aniline again, PANI, and this is their IV features. They wrote BIV with silver, and this is again some kind of stuff they had here. These two are fascinating. These are by the Zhao group at Texas. These are quantum dots, and these were done using remarkable technology, something that was facilitated by haptics. So have you heard of this? So haptics, essentially, let me just explain it a bit. So what they had, it is fantastic, almost science fiction. They were actually drawing on a cell phone, and whatever they drew, it actually got patterned by the bubble. So how was this done? So the cell phone essentially was interfaced to a computer, which basically did nothing but move the translation stage. So finally, this is not too tough. But if you think of it, it is amazing, right? You're actually drawing patterns on the phone using a stylus, and that information goes to a computer. That computer controls the way the stage moves. And they also showed that depending on how slowly or fast you moved, you actually got, so if you moved very fast, you got these kind of discrete patterns. If you moved very slowly, you actually got these continuous patterns of these cadmium, I think it was sulfide, cadmium sulfide. Let me see what it was. Yeah, what it was. It is either CDSE or CDS. Anyway, so essentially, if you move very slowly, you got continuous, which is understandable, right? You move very fast, the bubble just jumps, right? You don't give time for accumulation. So here you see these colors have changed. And you know why? Because when I actually have bigger, continuous patterns, the individual sizes of the quantum dots change. And with that, there is something called the Purcell effect, because remember, this is essentially an absorption re-emission process, essentially quantum mechanical. And the Purcell effect says that the emission lifetimes are affected by the environment. Or it also, so here that is there, but it's also the fact that because you have small particles, I mean, the size of the quantum dots dictate their fluorescence. Because you have smaller sizes, you actually have yellow here. Here you have larger sizes because you're doing slowly, and these dots sort of assemble. Some of them come together, and you have these small clusters, and that gives you blue. So in effect, finally, what you have, if I draw with a pen in a certain way, you get yellow. If I draw it in a different way, you get blue. It's quite fascinating. So this paper is here, JMCC. Next thing, this is something where we have done quite a lot of work, where we actually make catalytic chips. What is the meaning of that? You actually catalyze, pattern some catalysts. And then you see, for example, we have seen two things. So here we actually have a SOM and a this is called a porous POF. So yeah, this is a porous oxometallate framework. Okay. So essentially, this is some kind of a group of array of catalysts which we form in this pattern. Then we try to carry out this simple reaction of benzaldehyde to benzoic acid. And you see here that on the trail, we have this is Raman, we have a large formation of this benzoic acid. Outside the trail, you have almost nothing. See, here we tried this was, I think, done what we did was the epoxidation of styrene. Again, this was done on different catalyst, MO07. And here, again, you see that this is where you have styrene epoxide form on the trail. Outside, there's almost nothing, right? Here, this was, I think, done by the Zhao group. They actually wanted to change, some nitrophenol, p-nitrophenol to aminophenol, and this was in this NaBH4, and the presence of rhodium gold. These are the tracks are rhodium gold nanoalloys. So again, you can see that if I have this kind of a substrate, then you get maximum yield. Okay, so this actually tells you that you can make, what we want to do with this is make an array of such different catalysts on the same chip. And then you can have a host of different reactions all happening on the same substrate. Okay, so this is like, very exciting. You can make catalytic chips out of this, parallelize and both selectivity and you actually have reactivity both together. Okay, what is, however, one of the most interesting and what has, I think, the biggest thing for India, at least in here, because, with this COVID and all happening, we know how important low cost and, but sensitive diagnostics is. Very crucial, right? You are hearing all over the place. We are hearing nowadays, PCR the based tests and rapid antibody based tests, and there is a lot of suspicion about the rapid antibody tests because you don't know whether they are good enough. So this method, we actually envisage a way of enabling a new generation of these, rapid antigen antibody test kits by simply patterning the pathogen or the antibody which binds to the pathogen. But that is very tough because proteins are notoriously fickle in the presence of temperature. Because remember, when we have a bubble, it actually means the temperature around it is high. If the temperature is high, proteins will denature. So it's very tough. So what are the ways out? One way is you don't pattern the protein itself, but you pattern something else, some moiety which would act as a linker for the protein to come and bind. Other way is different. You sort of, this is the way we have tried, it is basically you have bubbles at very low power, inside laser power, I mean. So somehow, if you could actually just, twinkle the laser on off, have a small bubble. So while the temperature is hot, you don't, expose the protein at that high temperature for too long. So this has been attempted. Both of these have been attempted. This is what we had done, where we actually patterned this a composite of phototungstic phosphotungstic acid with SOM. But remember, the big advantage of SOMs is you can co-pattern a lot of things with it. So along with SOMs, we have actually patterned carbon nanotubes as well. I've not shown it, but we have done it. We have patterned a dye which just does not absorb at the laser wavelength of 1064. Perylene we have patterned. In fact, this pyrrole aniline that I was talking about, that all happened because we patterned it together with SOMs. Okay, so here what we did was we patterned this object, and that actually reacts with all these uric acid, glucose, ascorbic acid, but at different levels. So what we showed was that depending on how much this concentration of this we had, we could either detect uric acid or glucose, ascorbic acid, and we could also see that the fluorescence, result, the fluorescence of the patterns of these respective, so the pattern was done, and these were then drop cast, and then we saw the fluorescence of the resultant, combined. And we saw that the intensity was very different for all these things. So the urea, you can see that the fluorescence reduced. For glucose, it increased. For ascorbic acid, it did not increase so much. And you could actually see two pathways and all. That's more complicated. You look up the paper. This was done by the Zhao group, where they actually did an antigen antibody reaction. So, but then they did a very interesting trick. So they actually used this perfluorocarbons, and especially they use this perfluoropentane, which has a boiling point of only 30 degrees. And yet it mixes with water. So the thing was, you had a bubble at 30 degrees. It was remarkable, right? So used very, very low power. Okay, so very low power. So that basically grew a bubble. It's not shown here. You cannot see here. You see here. So what they did was this classic biotin streptavidin reaction they tried out. So essentially, they had initially, streptavidin in their dispersion. They grew a bubble. Streptavidin came and assembled in this ring. Then they passed biotin, and they could see a change in fluorescence. So biotin streptavidin reaction they did. We have actually done something slightly better. We've not published it, so we're not discussing it too much. We have actually patterned GFP. So GFP is green fluorescent protein. Those interested in biology might have heard of it. Very, very commonly used biomarker. Itself is a protein, and it's a very high molecular weight protein, which is very difficult to pattern by any other means. What we did was we took this ammonium tetrathiamolybdate and co-patterned it with my GFP. And then what you see here is this is GFP green fluorescence. Then we came with a secondary antibody. And if the secondary antibody actually had sort of had binded with GFP, sorry, the fluorescence will change. And it did change. So you can see that this antibody is actually secondary one was actually red tagged. And what you saw was basically red fluorescence. And if you actually used a filter, you actually got yellow fluorescence. So this tells us that we can actually pattern a protein and have a reaction with the second protein, keeping both of them active. And so these were actually, you watch the thing afterwards. Otherwise, you get things all over the place on the glass, right? So we actually got the activity of the protein retained, and this is of great promise. We have patented this. At the moment, we are actually trying directly on a pathogen. We are actually trying on influenza, and then let's see what happens. Okay. This is the future. This is what I envisage. At the moment, science fiction, but this probably can be done. Microfluidic chip, all of these are, so suppose I come in with this very ambitious way of, I have some patient has an unknown disease, right? I take part of his blood or serum or something, some serum, and I flow it to this channel. Now, these cross channels are filled with antibodies of different pathogens, of different diseases. Maybe this has COVID, maybe this has, I don't know, dengue, maybe this has typhoid, whatever. So the hope is that whichever the disease is would bind to one of these in particular. And I would see fluorescence coming from there. And that would be fantastic. I hope you agree with me. I mean, we are a very, very long way off from here, but this is the dream. Okay. So future directions, I'm coming to the end, I'm done. So as you said, so we want to make heterostructures, electronic devices. For that, what is essential is to pattern one thing over the other, because you need PN junctions for transistors. So that is something we are doing. We have got some success. This is the key of patterning anything mesoscopic. So one thing you have to realize, this method is such that whenever you have a bubble, you will have a flow. You will have material that will come and assemble, but will they stick? So what we saw with carbon nanotubes was that we could nicely pattern them. The moment we remove the bubble, they go back to solution or dispersion. But if we can make some material do something, some surface engineering, where what we want to pattern sticks, that is fantastic. Of course, diagnostics of pathogens, absolutely. And then we need to understand theoretically what is happening. because we do not still yet have a clear idea of why, for example, I don't really know. Maybe this question has come to some of you. Why do these gold and silver, when we actually pattern them, why do they stick? Right? This may be a case of, there has to be some hydrophobicity, hydrophilicity involved somewhere, something, but it's not been done yet. I mean, it's not clear yet. Why is that the SOMs or some of these materials, what is the quantitative pathway in which they actually undergo this phase transition? So as you can understand, this is a research field which requires everything, because optics creates the bubbles. Microscopy optics combination creates the bubbles. Material science dictates how patterns will be formed, how they will stick, how they will react with light, everything. Instrumentation, you saw that haptics, fantastic. And of course, chemistry, biology, proteins are biology, chemistry, of course, proteins, catalysis, everything. So you can completely understand this is one big reservoir of all fields of science it requires. And I think I can tell you with confidence that we have only uncovered the tip of the iceberg. The rest of the mountain still lies submerged inside the sea of uh, ignorance or not knowing, and has to be uncovered. Okay, this was the paper that has everything. This was published, finally published this year, I think in January, but it came online last December. So if you want it, whatever, up to the state of the art research in this area, you will get to know. You can get it, if you want it, I can send to you as well. And that's it. Thank you.
Thank you, sir. Thank you for your very interesting presentation. This made us very involved in drivers in micro bubble fabrication, especially haptics. Of course, it gave us feel attending the offline talk. Thank you so much, sir.
Yeah.
Now the session open for the question. Participants who have queries can unmute and then talk.
Yeah.
Clarify your doubts.
So, good afternoon, sir. This is Justin from NIT.
Okay. Hello, Justin.
Thank you for passionately explaining all the concepts, and I think now I could see your passion for teaching, and especially reaching out to students. Thank you for that. So,
Yeah,
may
welcome.
I request you to kindly explain about the future prospects in this research area, maybe for youngsters or students.
Yeah. So basically, this particular area, as I said, so we are trying to kind of, sell it as I mentioned in these things. So you can basically make, so, photolithography, e-beam lithography, those are there. Those will not get challenged by this. But what this actually helps us is to make these structures of very, very small length scales of anything without any sort of, very lot of effort in, say, mask preparation or anything of that sort. I mean, so if you think of it, it's very simple, right? You basically take some kind of a dispersion, which can be water, which can be some other thing, where the particular material that you want to pattern, that sort of is like, it's like sort of floating around. And then you use light, which is which is absorbed by that material you want to, right? And that straight will create some of this, this small bubble, micro bubble, and that will create self assembly, and that will just allow you to write. So this is essentially writing using a laser. This is some kind of a laser writing technique. Okay, only your pen is the bubble. So there are, the Zhao group actually had called this bubble pen microlithography, but we had done it earlier. We had a SPI paper where we saw actually, maybe SPI, one of these conference papers, where we talked about how microbubbles can be used as pens. I think all experts in the world sort of, we agree now that these are like pens. So using a bubble as a pen, you can write so much. And the interesting thing is this is one potpourri of research, right? Because sorry, it allows you, it requires, immensely interdisciplinary research. I can tell you that we are at times, suffering because I'm not a biologist, neither am I a chemist, right? So I don't have a sample, bio sample wet lab preparation. We don't have a wet lab. I have to depend completely on others. But then if I have people who are sort of passionate in taking this forward, because if you can really pattern proteins, that gives us enormous scope to study them, to study drugs. Because think of it, if you have proteins available uh, without the necessity to, use amplification, this PCR and all that, we already have them available. And it's like, these test kits, these rapid antibody test kits, which we can make in the lab, which we can ourselves draw almost. So essentially, a physicist can become a biologist, can become a chemist, can become everything. So my student Anand, who's working on this, he needs to know everything now. So this is one area of research where if you indulge in it, you become an expert in all the sciences, because there is no way out, because it requires all the sciences, right? You need, as I said, you need, optics. Of course, my light is what is creating it. You can make exotic forms of light and make exotic patterns. You need, of course, a microscope. The only necessity of a microscope is that you have a high numerical aperture objective, because that 100x, because 100x gives you small focal spot, that gives you, large absorbance because the intensity is so high, and that grows a bubble. You can do it, you can make the setup yourself. Okay, but then the imaging, etc., comes free with the microscope. It's inbuilt, so it's not too much of a hassle. You can do it. The most important thing for students that I feel is that this is one area which makes you, aware. So you can do very fundamental research with bubbles as well. I've not talked about that at all. You can do still very, very interesting non-equilibrium statistical mechanics studies, which we are doing also. But this lithography is a field itself now. But it's young. But because it's young, there's a lot of things left to explore. As I said, we have the iceberg whose tip you can see. The rest of the mountain is hidden in the sea of our ignorance. Yeah, I hope that answers your question.
Yeah, thank you very much. I also had one more question in mind, but I think that same question was posted by one Dr. Ramesh Kumar in the chat box.
Let me
His
just
question, I
get
just
out.
want to ask that question to you by Dr. Ramesh Kumar. He's asking, like, no, he's working in nanobubbles in area in various aqueous solutions. So, but he's asking, whether any evaluation method is available to detect or count the nanobubble, and if it is available, means what sort of method?
No, I'm sorry, I missed that. What nanobubble?
No, he is on Dr. Ramesh Kumar. He is working in the area of nanobubble. And he wanted to know whether any evaluation method is available to detect or count nanobubbles.
What? I'm just missing that thing that you're saying. What kind of nanobubble you're saying? Hard nanobubble.
Telling about bubbles, maybe in aqueous solution, you may get.
Oh, count the nanobubble. Okay, I saw the chat. Okay.
Yeah.
Count. No, so detect is mostly by scattering. Okay. It is almost entirely by optical methods, where so nanobubble. So see, so this what we do is using the bubble for a certain application. Okay, so we use only a single bubble here. Okay, but and this bubble, see, microscopically, if you think of it, the resolution of a microscope is the diffraction limit. So, for example, we can easily see objects. So, if you think of the diffraction limit, that is given by lambda divided by twice numerical aperture. So, our Lambda is about 1064. Numerical aperture is about 1.4. So roughly it comes to around 400, 500 nanometers. So you can anyway see them. So if you use a 1.3, 1.4 nanometer, I mean 4 numerical aperture objective, then you can anyway see bubbles which are, so you can see at the level of about 300, 400 nanometers. You can see, you can optically make out up to like half a micron without too much of difficulty. Now, if you cannot see them, if they're even smaller than that, then the only hope is some scattering. Then basically you need to look at the scattering pattern, and then you have to have some kind of input, simulation or something by which you sort of match your experimental result, and then from there you can probably find out the number of bubbles. But the diffraction limit essentially is anyway in the hundreds of nanometers for high numerical aperture microscopy. Okay. And Acha, so the next question I see for books. So books, so I can only suggest our review. So in Nano Letters that has been published. So this is very young a field. So at the moment, I know maybe 10 years from now, if it grows, sorry, in the way it is growing now, maybe we shall have a book. At the moment, I can suggest that Nano Letters paper, because we have like 75 references, I guess. And it's very exhaustive. So whatever is happening in this field, you can make out. Yeah. Any other question?
Hello, sir.
Yeah.
Sir, I have a question. First of all, thank you for the colorful presentation.
Thank you. Welcome.
Sir, what is the advancement in haptics in comparison with the older techniques?
Yeah, haptics is something. See, when I used to work in General Electric, GE, I hope maybe you've heard of it. So GE is a very, very big company based in the US, but they have this massive global research facility at Bangalore. So this was in around 2007. I heard a talk by this faculty of MIT who had come to our center, and he actually told us that so haptics essentially is transfer of touch. Okay, for people who do not know it. So he actually showed us that they were and it's essentially made out of your MEMS, MEMS, maybe you've heard of micro electromechanical systems, MEMS technology, and very, very small pressure sensors, and things like some transducers. So what he showed us there was that he had managed to make this device where he could transfer touch, in the sense that there was this kind of a pad which was filled up with these sensors which could measure any differences in pressure. So suppose you press with your fingertips, the differential pressure at all points of your fingertips would be measured and then would be wirelessly transmitted. And then there would be a receiver which to another person, you would basically, that person would perceive the signals by placing his or her hand. So that essentially meant that I could sort of feel your touch. Okay, so that was back, remember, in 2007, where he told us about that. This was like more than a decade, 14 years back. So now when I see this Zhao's paper, I think it has gone to a level where you can, things, they have these interfaces where directly mobiles can actually, when you write on a stylus, so that is essentially some pressure you're applying on the LCD screen, right? And that gets sort of translated to a computer. You can interface a mobile with a computer very easily. Android system, you can, very easily, it's a very receptive system. So that you can do. So see, I'm not an expert in haptics by any means. I can only tell you that the fact that you can actually control a translation stage by writing on a mobile phone, that tells me that haptics has reached a level where I think transfer of touch is going to be happening very soon, where maybe 30 years from now, whenever, sometime, maybe some surgeon can be, performing an operation without being in the chamber. I mean, that is very tough. But if you can actually, make, have robotic arms which can be operated by somebody, at some remote location. Yeah, so I actually can sort of move my hand and I can feel the resistance from tissues and all kinds of, organs or something. I can move accordingly, right? And that arm can move as per my pressure, my speed, and, do precision stuff. That is very, of course, advanced, but I think that is where the, a very, very fascinating future for haptics holds.
Okay, sir. Thank you. I have one more question.
Yeah.
Other than water bubble, what other liquid media can be used?
Oh,
and
many
how
things.
it would affect the properties? And what are the major properties that it would affect?
Yeah, so one major thing that you have to avoid is volatility. See, water is not volatile, so that is very, very useful. Okay, so because if you take something which is volatile, then your sample, and it's like air, right? Because this is all in lab atmosphere. So basically everything will just evaporate, right? So you have to sort of ensure that whatever medium you're taking is not volatile at room temperature. That is very crucial. And also you have to also see that whatever liquid you're taking does not, is not light enough so that the material that you are wanting to pattern goes and sits at the bottom. The material has to float around. It has to be dispersed. Okay, so that is very true. Those are the two properties that we basically see, that it should not be volatile, that it should not all evaporate away. I mean, it's okay. Maybe you can, if it's like there for 10-15 minutes, you can probably finish, because this is very fast. I forgot to say that, but this whole thing is extremely fast. I mean, I can see this translation stage is moved at the speed of it can move at like tens of microns per second. Okay, so you can make the whole millimeter pattern okay, in say 100 seconds. Okay, so you can, whereas in e-beam something, you take days at times, very long. Most of self-assembly processes take very long. Here you can finish whole things in minutes. So your solution has to be, or your liquid medium has to not disappear in that time. That is crucial. And also your solute should not accumulate and sit at the base. I mean, it should not just all just sit at the, I mean, it should not just assemble at the, bottom of the thing. I mean, there should be something in the liquid floating around.
Okay, thank you very much, sir.
Yeah.
I think there is one more question in the chat box.
Okay, let me just see the chat box. Temperature. Okay, very good. So temperature is a very, very nice question. So it can go up to, okay, very, very important is, so if we see water, there is this thing called the critical point of water, which is about 647 Kelvin. Okay, so 647 Kelvin, you cannot have water absolutely at any temperature pressure. It cannot exist as a liquid. Okay, so this is something we actually saw in a very fascinating experiment. We have published it in, I think, New Journal of Chemistry, where we saw that, see, one very interesting experiment is to look at the diameter of the bubble as a function of laser power. So you can do it two ways. You can have the laser power, you can have the laser turn on, crank up the power and see how the bubble expands, how the shaping, I mean, how it becomes bigger. So that you see mostly a linear kind of thing, because you cannot really reach too high powers. But then there is the other one where you have a bubble at a power, shrink the bubble, that is turn off the laser, then turn on the laser at a higher power. Okay, so you keep on growing new bubbles at higher powers, and there you have fascinating stuff happening. What we have seen is that the bubble first grows linearly with the laser power, then it becomes flat. I mean, you increase the power, but the bubble size does not increase too much. And then suddenly the bubble just explodes, and we see the whole computer screen that we have just filled with the bubble. It just explodes. And what we realized was that we were actually cranking up the temperature actually. So laser power means temperature. So at one point, so there is a difference between the base of the bubble and the top, right? So that at one delta, that is difference, you actually have convective flows coming in, and they start taking some of the heat away that you're putting in. And because of that, even if you increase the power, the bubble doesn't grow much. But if you go beyond a certain power, that is close to that 647, that the temperature of the base of the point where you are hitting the laser, hotspot as we say, that is around 647 Kelvin, close to that. That is about 350 degrees, 370 degrees centigrade, right? Then the liquid itself has close to zero surface tension. Water starts, evaporating explosively. Explosive evaporation of water. And that tells you that for a water medium, you certainly cannot go at temperatures higher than about 600 Kelvin. The lowest, of course, that we have seen at the border, at the bubble water interface, is around 110 degrees, around that. But that can be, you can say that then proteins will anyway get denatured. Thing is, if I do it very quickly and have a small bubble, so that proteins assemble, and by the time they know that the temperature is so hot, I switch off the bubble or move it away. That is something that might work. The temperature is typically, as I said, it is boiling, so it is about 100 degrees, 105 degrees, 10 degrees. It can go to a maximum of about 370 degrees centigrade in water.
So how did you measure this temperature?
So that so I can tell you that we have not measured it directly. Experimentally, we have not measured. You can do it by dyes. We have a model by which the thing is that the conductivities of water and all that, thermal conductivity, viscosity, all that So we had a model in place, and we also had that mark where we know that the bubble was exploding like that. Okay, so we know that that had to be close to 647 Kelvin, right? So that was like a marker for us. So we have a calibration of the laser power, knowing that the bubble grows at around 100 degrees, and the highest you can reach is around that. So after that, it's a matter of calibration. It's a fact that we have not measured the temperature directly. You can probably do it in using COMSOL. COMSOL, maybe some of you have heard about it. It's a very nice multi-physics modeling software. So you can give, so COMSOL has a fantastic library of all these different materials. So if you give a particular material, then it will tell you the temperature. So experimentally measuring is challenging. You can use dyes. People have done it, but it's not so obvious because, if you don't have you have to have a dye which is going to stick to the bubble, and if it sticks, it should not, sort of burst the bubble or something. It's not very obvious, but it's not very simple. But I think the Zhao group or somebody, I think somebody has done it. But we estimate it using a mixture of simulation and experiment.
Thank you, sir. That's very clear. Thank you.
Is there any other questions from audience? If no more questions, I thank you, sir. Thank you very much for your valuable time
Welcome.
with us.
I really enjoyed this experience as well. So we will be having probably a conference at ISER, in May, June or something. So I will surely get in touch with you. I'll ask the students to get in touch with you. Okay.
Thank you, sir. Thank you.
Yeah, welcome. Thank you so much.
Dear participants, feedback link is given to the chat box. Kindly fill it. Otherwise, it will expire at 12:40. Thank you. Thank you for being with us.